Okay, so we are starting Module 11, which is two sample T procedures. We are going to be doing hypothesis tests and confidence intervals, and we are going to be doing the pooled hypothesis test on the difference of means. We're going to be doing the pooled confidence interval on the difference of means. Then we're going to do the not pooled or Welch's hypothesis test on the difference of means and the same confidence interval. And then we're going to be doing the matched pairs hypothesis test and confidence interval. And um, we're going to start with the pooled version. So let's talk about the setup we have here. So generally, in the two-sample hypothesis test or confidence interval of the means, we're interested in determining if the mean of one population is equal to the mean of another population. So mu1 is equal to mu2, or if their difference is 0, which would be mu1 minus mu2 is equal to 0. We take a sample from each population and conduct the hypothesis test or confidence interval. In the two-sample difference of means procedures, there's a numerical variable of interest. The mean comes from this, and then there's a categorical variable as well, and that separates the numerical variable into two different groups. So let's talk about an example so you can see what I'm saying. Is the diameter in red cedar trees different from the diameter in Virginia white pine trees in the Jefferson National Forest? So our numerical variable is diameter, and the categorical variable is tree species. And specifically, we have two tree species here. The diameter is our response variable, and tree species is our explanatory variable. So we have one variable that's categorical with two levels. So we've chosen two different types of trees to compare. And then we have a numerical variable for each of those categories. The parameter is the difference of the population means. So the null hypothesis is that the mean of red cedars minus the mean of white pines is equal to 0, or because we're saying that these things are equal to 0, I can just move my mean to the right side and get rid of the 0. So the null hypothesis can be written mu red is equal to mu white. And that's oftentimes how we write our hypotheses. For the confidence interval of this same scenario, we're looking for lower and upper bounds that estimate the difference between the mean of the red cedars and the mean of the white pines. So what we're looking for is um, a lower and upper bound that tells us how far apart the difference of these two groups of diameters are. There are two versions of the two-sample T procedures. One that assumes equal population variance, this is the pooled T procedures, and one that does not assume equal variance, this is the not pooled or Welch's T procedures. These procedures both have different test statistics, degrees of freedom, and conditions. We're going to start with the pooled or equal variances two-sample hypothesis test on the mean. To develop our hypothesis test, remember we need our hypotheses, the conditions that we have to meet to determine our test statistic, and the underlying sampling distribution and the formula for that test statistic. So the two-sample T hypotheses can be written in multiple ways. Mu1 is equal to mu2 as the null, and then the alternative is mu1 is not equal to mu2, or mu1 is greater than mu2, or mu1 is less than mu2, Or we can write these as subtraction statements. So we compare the two populations by setting their difference equal to 0. Just an FYI, this can be another number. So we could say that the difference in their diameter is more than 22 centimeters. And so that would be 22 instead of 0. Although, to be honest, I've seen like textbook questions like that. I've never seen it in real life in all the consulting I've ever done. And even when I worked in industry, I've never seen that either. All right, so our null hypothesis when we write is a subtraction statement, is that mu1 minus mu2 is equal to 0. And then the alternative is that mu1 minus mu2 is not equal to 0, is greater than 0, or is less than 0. The conditions for this pooled t procedure, both the confidence interval and the hypothesis test for the difference of means, is pretty extensive. So let's go through all of them. We have to have a random sample or two random samples. We can take one random sample and separate by category, or we can take a random sample from each of the two categories. Sample sizes are equal or nearly equal. So we have random sampling, and we have N1 is approximately equal to N2. I will warn you that there's no rule on what equal means. So is 10 equal to 12? Most of us would say yes. Most of us would say that 7 is equal to 9, but we would also say that 70 is not equal to 90, but 7 and 9 are just as far apart percentage-wise as 70 and 90. So this is one of those gut checks that we just have to make a decision. Normality has to be met, and T procedures are robust to departures from normality. So all we have to do is just get close, you guys. If we're close, these T procedures are good enough. So our third condition is normality. And how we satisfy normality here, we have the rules we had in the past, but we have some new ones. So each sample is normal because you're told so. So that's just the one we know in the past that historically our variable is normal. Or we're using a word problem, we're just told it's normal. Graphs of each of the sample are bounded and symmetric. And so you have to do graphs of both variables. Graphs of each sample are similar in shape without any big outliers. So this is a new rule. So I could have two skewed right distributions, and as long as I don't have any big outliers, this will still work. This test works fine, even with skewed data. And then the last condition is that we have large samples. We're going to apply the central limit theorem, but once again, we have a new rule. And instead of n is greater than 30, we just have to show that n1 plus n2 is greater than or equal to 40. So the sample sizes of the combined categories have to add up to 40 or more. Then the samples are independent. That means the data is not paired, and our sample sizes are small compared to the overall population. And so this one is independence, or I typically just write not paired because we're going to be doing a paired t-test in a little bit. So you can write independent or not paired, your choice how you write that. And then the last condition we have to meet is population standard deviations are believed to be statistically equal. And like all conditions, you have to show this. But to show this, we have to use our sample standard deviations because we don't know population standard deviations. So we use this following rule of thumb. We're going to show that S1 over S2 is less than 2, and S2 over S1 is also less than 2. And by the way, this is population. Standard deviations are believed to be equal, so sigma 1 is equal to sigma 2. Or some people will say it's the variances are equal, so sigma squared for each of the two populations. are equal to each other. But we use sample standard deviation, not variance. So I typically just use standard deviation here so that we remember which thing to use. All right, so that's a lot of conditions to satisfy. The test statistic, remember our test statistics often follow the format of statistic minus parameter over standard error of statistic, and that's exactly what we have here. If the conditions on the previous page are met, the test statistic for the pooled t-test on the difference of means is an approximate t-test statistic, and our test statistic is equal to the difference of sample means, so x bar 1 minus x bar 2 minus the difference of population means, mu1 minus mu2. But this thing here, mu1 minus mu2, is almost always 0. And so because of that, it actually drops out of the test statistic. And then that's all divided by our standard error of our test statistic. And that is the pooled standard deviation of the two groups, because we said that these standard deviations were equal. We actually have to calculate that. Pooled standard deviation formula is down here. And that is multiplied by the square root of 1 over n1 plus 1 over n2. So our test statistic is x bar 1 minus x bar 2 over the spooled standard deviation of the two groups times the square root of the quantities 1 over n1 plus 1 over n2, where x bar is the average of each sample. Mu1 minus mu2 is the value of the difference in the null hypothesis, which is almost always 0, so it drops out of the test statistic. SP is our pooled standard deviation. The formula is below. And n is the sample size for each sample. The degrees of freedom associated with this test procedure are n1 plus n2 minus 2, and we need these degrees of freedom for our t distribution because the t distribution changes with degrees of freedom or sample sizes, because as sample sizes get bigger, this distribution approaches the normal curve. The pooled standard deviation is equal to the square root of the quantity n1 minus 1 times the variance of group 1 plus n2 minus 1 times the variance of group 2 over n1 plus n2 minus 2. And of course, we're not going to calculate any of these things by hand. We're going to let R do it for us. And then the equal variances or pooled two-sample t confidence interval is an estimate of the difference of means. So we are trying to estimate mu1 minus mu2, and we use our test statistic to calculate this confidence interval. Our lower bound is x bar 1 minus x bar 2 minus t times the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. And the upper bound is the exact same thing, but we're adding that margin of error. So t times pooled standard deviation is margin of error in both cases, and x bar 1 minus x bar 2 is our statistic. So we still have that same format of statistic plus or minus our margin of error. We'll do the same steps we've been doing for both hypothesis tests and confidence intervals. However, the details of those steps change. Really quickly, I just want to point something out because this is going to show up later. If 0 is in our confidence interval, then mu1 is equal to mu2. If 0 is not in our confidence interval, then mu1 is not equal to mu2. So that's one of those things where when we're comparing hypothesis tests to confidence intervals, this is what we're looking at, is are they equal or not? Well, if they're equal, 0 is in the interval. The conditions for this confidence interval are exactly the same as the hypothesis test. conditions are the same as the hypothesis test. All right, so when we do our hypothesis test, we're going to do the same 5 steps. We're going to write our hypotheses, we're going to calculate our sample data and pull out, write some graphs, satisfy conditions. We're going to conduct the test, calculating our test statistic and our p-value. We're going to make a decision to reject or fail to reject the null, and we're going to state our conclusion about the alternative. But what we do in these steps changes. So we write our hypotheses, and the null hypothesis is going to be that mu1 equals mu2, or you can write it as the subtraction statement, mu1 minus mu2 is equal to almost always 0, but could be a different number. We collect our sample data and we state or calculate all necessary information, and we graph our data to satisfy our conditions. So what stuff are we going to need here? There's a lot, you guys. So remember, we are calculating this test statistic back here, or we're calculating this confidence interval. So what we need is we need the sample mean for category A and the sample mean for category B. So we need X bar A and X bar B. We need sample size for each category, so N sub A and N sub B. And you can use 1s and 2s here instead of A's and B's if you want. Sample standard deviation for each category, so S sub A and S sub B. We need our level of significance or our percent of confidence. Remember, alpha is almost always 5%. We need a graph of each set of data by category to show normality. If you aren't told normal and you can't use the central limit theorem, you have to look at each of these, even if you can meet normality another way, just because you want to look for major outliers that may be mistakes in data. So what graphs can we use? Well, we can use the histogram for group A and the histogram for group B. And if you do a histogram for one, you do a histogram for the other. Or you can use a QQ plot for group A and a QQ plot for group B. And again, if you do a QQ plot for one, you do a QQ plot for the other. Or you can use a box and whisker plot for group A and a box plot for group B. And again, if you do a box plot for one, you do a box plot for the other. So this is what we're doing when we're looking for normal. And we have to look for normality for each one. But in addition to this, we also have to make a graph of both samples by category on the same axis. So this is new. We're actually adding an additional set of graphs, but this graph, you guys, is going to be on the same axis. So we want to do a graph that has a box and whisker plot for group A, and let's say a box and whisker plot for group B, and they are on the same coordinate grid. This is a stacked or double box plot. So it's still called a stacked box plot. It's just also called a double box plot because we only have 2 categories. Then we conduct the test, calculating our test statistic and our p-value. Our test statistic is a t-test statistic, and our p-value is the other thing that we need. And then we make a decision. Remember, we reject ho if our p-value is less than or equal to our level of significance, and where certain fields will reject ho changes depending on the scenario you have. And then you state your conclusion about the alternative hypothesis. If we reject ho, there is evidence for ha. If we fail to reject ho, there is not evidence for ha. For our confidence interval, we collect our sample data, we state and calculate all of our necessary statistics, and we graph each of our sets of data and then the combined set. So the graphs here are the same as the hypothesis test. So we're going to have three different graphs, one for each category, and then one with the combined box plots. You're going to satisfy the conditions, which are the same as the hypothesis test for the pooled test. You're going to calculate your confidence interval using technology. So we're getting a lower bound and an upper bound. So two different numbers to tell us what the bounds are on the difference of means, mu1 minus mu2. And then we interpret our interval. But when we interpret our interval, you guys, the words change just a little bit. I am blank percent confident, so 95% or whatever, that the difference between the two population means. So the difference between the population means mu A minus mu B is between my lower bound and my upper bound. All right, so we've gone through all of the details. Now let's do an example. All right, an observational study comparing two brands of batteries was conducted. We wish to know which brand is best based on hours of life. We've purchased 20 of each brand from multiple stores trying to randomize. Does one brand work better or worse than the other? Conduct the appropriate hypothesis test to answer this question. The data can be found in the battery's Excel file. Before you start the hypothesis test or confidence interval, you want to look at your statistics and the side-by-side box plots, as well as graphs of normality. The R code can be found in your Module 11 equal variance battery file. So our hypotheses, we're just going to write these down. Our hypotheses are going to be the mean of battery A is equal to the mean of battery B. And we are interested in if they work better or worse. So the alternative is that the mean of battery A is not equal to the mean of battery B. And we could have written this as a subtraction statement. So mu sub A minus mu B is equal to 0 for the null. And the alternative would be mu A minus mu B is not equal to 0. Your choice which way you write those. For our statistics, we need X bar for A, we need S for A, and sample size for group A. We need sample mean X bar for B, sample standard deviation for B, and sample size for B. We're going to need our graphs. So we're going to need the histogram or the QQ plot for A and B. And then we're going to need our stacked box plots as well. And those are going to be on the same axis. And we'll come back and deal with our conditions after we get these statistics in R. So let me move to R. I've already imported my data, and we're going to quick look at this data. So there are 20 observations of two different variables. The variables are brand A and brand B, both of which are numerical because we have how long they lasted. Brand A has a bunch of battery numbers, how many hours they lasted, and brand B has how many hours they lasted. And I pulled that data in, and so now I just want to calculate my statistics. So I have the mean of batteries brand A, standard deviation of batteries brand A, and sample size. I used length for batteries of brand A, and I did the same thing for brand B. So I'm going to run that code. And so I have my means, my sample sizes, and my standard deviations. So I can put that in the notes. The sample mean for A is 15.64. Sample standard deviation was 1.94. Sample size was 20. For brand B, it's 15.025. Sample size was 20. And sample standard deviation was 1.67. We want to take a look at some graphs. Oh, by the way, I also satisfied conditions here, but I'll come back to these in just a minute. The histogram, I'm going to look at these histograms real quick. And you guys, I don't really need to use good graphing skills here because I'm just looking to see the shape. So I'm going to run this data. So when I look at battery brand B, this is clearly bimodal, but there's a peak in the middle and there are no major outliers. And the same thing is true with brand A. There's a peak in the middle and no major outliers. So both of these would be normal enough for the T procedures because they're so robust to departures from normality. And let me come back to this. So my histogram and QQ plots have a peak in the middle and no major, they actually don't have any outliers. So let me just write no outliers. But I also want you to notice that the sample sizes are 20 for each one. So that's going to allow us to meet one of our conditions. So let's work on our conditions now. And we'll come back to the graphs in just a sec. So we need, remember, I'm going to go back here, you guys. There are so many conditions. There are 5. We need random sampling. We need approximately equal sample sizes. We need normality, either one of these methods. We need not paired or independent data, and that the variances or standard deviations are approximately equal by showing that the proportion of the sample standard deviations are both less than 2. All right, so conditions. Random sampling, N1 is approximately equal to N2. We need normality. We need not paired data or independent data. And we need that sigma A or sigma 1 is equal to sigma 2. And we have to start working on these. Well, I already know one of these. Sample sizes are perfectly equal, and we were told that they went to different stores to try to randomly sample. Normality is also met by the central limit theorem because n1 plus n2 is greater than or equal to 40. Or you could use the graphs. Both of these are good enough for normal. So that condition is met. We do not have paired data. We just have 20 of each battery, but they're not paired together in any way. And then for sigma 1 equals sigma 2, we have to show that S1 over S2 is less than 2 and S2 over S1 is less than 2. And I've done that in R, but I want to show you where it's coming from. Whoops, was not what I meant to do. I touched my screen. My standard deviations are 1.94 and 1.67. So 1.94 over 1.67 and 1.67 over 1.94. Well, the smaller one over the bigger one is always going to be less than 1. So that one will always be met, whatever the smaller one is. So you only have to look at the proportion of the big one over the smaller one. So we did that. I did that in R, and that's done here, testing, do we have equal variances? I did the standard deviation of proportion 1 is standard deviation of A divided by B, and standard deviation proportion 2 is B over A, and I'm going to run those, and you'll see that the proportions are 1.16 and 0.86, and so they are absolutely smaller than 2. So this one was 1.16, and this one is way smaller than 2. It doesn't matter, but we have met the conditions to do a pooled procedure. So a pooled T procedure, we could do the t-test or the t-interval. Now we need to go back and we need to look at our stacked box plots. We haven't done that yet. So the stacked box plots, the code for that is here, but I do want to point out, this is stuff way back from like module 4 when we were doing 2 category data. So I did the batteries of brand A, comma, batteries of brand B. And then I did a title. I put the names in so that I could get them on my legend. I did a color. I have to have two different colors for my box plots. I use the rainbow function here. You can use a rainbow function, or you could do a matrix, sorry, a vector. You could do color equals C, parentheses, and then color number one, like light blue in quotes, comma, color number two, like dark blue in quotes. And then your X label, your limits, and I want mine to be horizontal. You don't have to do that. When I look at these graphs, what I notice is that these graphs overlap each other significantly. The medians are not very far apart, so that indicates to me that these battery lives are probably very similar. And so this graph we would pull into our code, and then we would pull the graphs from R here. But real quick, these graphs, when I look at these, brand B has a median that's a little bit lower, but they almost completely overlap. And brand A has a median that's a little bit higher, but they almost completely overlap. So a little bit lower. Whoops, that's not really skewed. And then the other one looked sort of like this. It was just a little bit higher, and it went a little bit higher here. Um, and so now we've met the conditions, we've done all of our graphs, we can actually do the test. So we're going to do the pooled t-test. And we want to get a t-test statistic and a p-value. And I'm going to let you guys spend some time reading this, but the t-test notes are here. You have to put in your dataset $variable1, dataset $variable2, and make sure that these are in the same order you wrote your hypotheses in. And the reason for that is if you have a less than or a greater than alternative, the order matters. Mu is the difference between the two means, which is almost always 0. We say that paired is equal to false until we get to the third test in this module. Variances are currently equal. We just showed that sample sizes and variances were equal. Our alternative is a two-sided alternative, but it could be less than or greater than. And then our confidence level, if you're doing a confidence interval, you want whatever confidence level you have. You don't have to have that there. I always put it in associated with alpha. So my t-test code is here. You guys can take a look at that when you get a chance. I'm going to run that code. And I've done the hypothesis test. My t-test statistic is 1.0754, and my p-value is 0.289. That's a big p-value, no surprise there. T-test statistic 1.0754, my p-value is 0.289. And remember, we're using a t-distribution here. Looks sort of normal, just has bigger stuff in the tails. 1, 2, 3, 4, 1, 2, 3, 4. When we have a two-sided test, we're looking at the absolute value of t. 1.07 is, whoops, not quite that far out. 1.07 is like here and here. And so we have to do p-values from area on both ends. That p-value is 0.289. So that's, whoops, I have no idea what I just did there. So now I'm going to make my decision, and this is just the same rules we've had before. We compare our p-value to alpha, and we're going to use alpha of 0.05, but it doesn't matter. We could use 0.10 or 0.01, and we'd have the same rules. P-value of 0.289 is a big p-value, so we fail to reject O. That's no surprise because remember the medians and the distributions pretty much overlapped each other all the way through the graph. And so our conclusion is that there is not evidence at any reasonable alpha level, to be honest, because our p-value is 0.289, to show mu of battery A is not equal to mu of battery B, we do not see a difference between the brands. All right, so what do we do if we cannot show that we have equal population standard deviations and nearly equal sample sizes? That means, what do we do if N1 is not approximately equal to N2? Or S1 over S2 is less than 2 is not true. Or S2 over S1 less than 2 is not true. But we can show that other conditions exist. We use another version of this test called the two-sample T procedures. Specifically, we use the one that does not assume equal variances, and that's called the not pooled Welch's T procedure, which we will do next.